In this lecture, we are going to discuss the observability of the system. This is very, very important part for designing the control, state feedback control. And also we'll look the mathematical formulation of the observer. Before we proceed to the lecture main contents, let me highlight some important points. Let's assume we have whatever the control algorithm we have developed for the plant to be controlled. So let's assume this is the plant. We are having plant and we have the controller here. And controller provide the ideal control input to the plant to be controlled. And we are having the X is output, plant output. So let's assume this is our X dot equal to f of X sum system. And we are having the summing point where we get the comparison between the desired values and actual state, X desired, and sensor provides the states for designing the state feedback control. Sensor block. Now the question is, if you notice our system is system output y equal to cx, right? And this is error. And also we are designing the controller y u equal to a into x desired, sorry, x desired minus x, right? Now, if you notice here carefully, this is the state are used to design control U. Now, how are we going to ensure all the states are available for us to design control U? Because if you notice here, we are assuming in our previous examples that all the states are available to design control. That's why we are saying that this is state feedback control. State feedback control. So we have to ensure what are the states that are available to us for designing the control. Whether if any of the states are unavailable to us for designing the control, we need to estimate that state. So if you see this example, so here we are having system. Here we are having system x1 dot equal to minus 2 x1 plus 3u and x2 dot equal to minus x2 plus u. And if you and also we are having y equal to x1. So this is the dynamic system given to us. And if you draw the signal flow graph for this particular system, this is the signal flow graph we are getting, right? So here, if you notice y equal to here x1, y equal to x1. But this y is not in a y equation, we don't have the x2 parameter. So only if you consider here, for example, so only you are having x is a vector and y equal to cx. So y equal to only x1 parameter available to the sensor for measuring the state. So that's why x2 here is unobservable. But x1 is going to observed by the sensor here. So this is how we need to find the x2, estimation of x2, so that we can design state feedback control. So this is the main objective of this content of this lecture, how we can estimate or how we can find all the states available to us for designing control. So now, if you consider our um, the space aircraft equation for the rotational motion of the aircraft, for example, rotational motion of the aircraft. So here, uh, if you go back to our the equation motion, so this is the rotational dynamics equation. This first three equation, and this is the rotational kinetics, the last three equations. So if you notice carefully, in the rotational dynamics equation, we are only applying the control, which is L11. So L11 can be together with control plus disturbance, but here basically we are applying the control input to this parameter. And we are propagating, after applying this control, we are propagating the dynamic equation, where actually we are finding the state PQR. So this PQR going to this equation to solve phi theta psi. So we can say that here we have the measurement. We have the measurement PQR using, maybe we have sensor gyro, using gyroscope, but we don't have measurement for the Euler angles phi theta psi, but we don't have phi theta and psi. But since PQR phi theta psi is a function of PQR, I can write phi theta and psi, which are the function of PQR. So we can find phi theta psi indirectly, right? So here basically we can say these are the parameters are affected by the control input, but these are not directly influenced by the control input. So in this case, we can comment that phi theta psi are not directly observable as a variable to us. So estimating phi theta psi using measurement of PQR, we call it, this is actually the process we call it observability. Now, if you define the definition of the observability definition, when an observer estimates entire state vector, it is called full order observer. So in this case, we can estimate PQR. We can estimate PQR directly from the control equation. We can find PQR if you apply the control input to this equation. We can find PQR. So here we no need to estimate PQR, right? But we need to estimate phi theta psi for using this kinematic equation. So this is, we can say, when an observer which estimates only unmeasurable. So here basically we can say This is direct measurement. These are the parameter direct measurement from the gyroscope, but these are the state we can measure from the given PQR using this equation. So this is the observer which estimates only unmeasurable state variables. So for the present case, in pi theta psi is called reduced order observer. And another definition, a controller which generates control input, the plant based on estimated state vector is called compensator. So this is how we can define the definition of the observer and how we can define full order observer and reduced order observer and a compensator. So these whole stuff come under observer design for controller design. So now we'll go to the mathematical formulation of the observer, how we can test the observability of the system. So generally, observability of a system we can define based on the unforced system. So our given system is system dynamics. We can write x dot equal to x plus du and y equal to cx plus du. But for observability test, we only take x dot equal to x and y equal to cx. We don't take any control input in the dynamics. So for observability test, if you want to test the observability of a system, for observability test, we consider x dot equal to x and y equal to 6. So if you notice carefully, here we can take AMC matrix for testing the observability. Because x dot equal to x, it talks about the state, how it is propagated, and y equal to cx talks about how we can take the states for designing the control. This is basically output, and x is the number of states available in the controller in the plant, right? So now there is a similar to the contributed test, observability test. We can do some observability test matrix, which you can define as observability test matrix. Test matrix we can define as N equal to C2 A transpose C transpose. This C transpose to first element, and A transpose square C transpose with this. So if the rank of N, if the rank of N is found to be you can say, right, a matrix. full rank, then we can say system is fully observable. If you can't, if the rank of n matrix is found to be less than the order of the matrix, then we can say the system is not fully observable. Now let's take an example to validate this concept. The example. So let's assume we have a system matrix A equal to 1, 0, 0, 0, minus 1, 0, 0, 0, 5. This is the system matrix given to us. This is 5. And C matrix given to us 1, 0, 0, 2, 1, 0. So using these two matrices A and C, we can test the observability of the system, right? So this is, if you notice here, the system matrix is 3 cross 3. So we have to go till, we have to find C transpose, A transpose, C transpose, and A transpose square, right? And C transpose. So let's find this matrices. A transpose, we can say whether the system is observable. Okay. So here we need to find for C. So we need to find for C transpose. So C transpose we can find 1, 2, 0, 1, 0, 0. And A transpose we can find 1, 0, 0, and 0, minus 1, 0, and 0, 0, 5. The same as A. And we need to find now A transpose, C transpose, the second part of the A matrix, second term. So here A transpose, C transpose, we can find 1, 2, 0, minus 1, and 0, 0. And A transpose, the third term, A transpose square, C transpose is found to be 1, 2, 0, 1, and 0, 0. Right. So we can form the A matrix now. In, if you substitute all the element terms in A matrix, we have 1, 2, 0, 1, 0, 0, and 1, 2, 0, minus 1, 0, 0. And the third term 1, 2, 0, 1, 0, 0. So this is basically C transpose. This is A transpose, C transpose, and this is A transpose square, C transpose, right? This matters. Now let's find the rank of this N. Rank of N we can find it comes up to be 2. So, but it means rank is less than 3. So hence the system is not observable. So one of the state we can't observe from the output equation. So now we'll go to the mathematical derivations, how we can find the mathematical formation of the observability test. So here we are going to consider the system. Let's put the mathematical formation. we have the system, LTI system, x dot equal to x du and y equal to cx plus du. Why it is LTI system? Because the coefficient of x and u are assumed to be not time varying. So it is not function of time. That's right, linear time variant. Here also we are assuming the observer dynamics. How this dynamics is found to be, we'll explain. X dot equal to x dot equal to a naught x naught plus b naught u plus l y. Okay. That will be this equation number 1, equation number 2. So here O indicates for observer, and this dynamics is the observer dynamics, and this is the original system dynamics, right? So here L actually observer gain matrix. So here the matrices A naught, B naught, and L must be selected such that estimation error we can assume E naught equal to x minus x naught. This is the system state, this is the observer state, is brought to 0 in steady state. So once this condition is satisfied, we can see that all the states are available to us for designing the state feedback control. One important note, for designing the observer, the eigenvalues of the observer dynamics is chosen to be faster than the plant dynamics. So I can write here, for designing, why it is so, we'll explain why we'll be taking the example in more detail. For designing the eigenvalues, so here basically this is the, you can assume that this is the desired eigenvalues that will be chosen for the observer design must be faster than plant dynamics. It means the eigenvalues of the observer should be more negative than the eigenvalues of the closed loop system. If eigenvalues of the observer are chosen to be highly negative, then such observer would be highly sensitive to noise. Actually, in practice, observer eigenvalues are chosen so that they are 4 times. So basically, we are 4 times more negative than the digital closed loop performance. So here, originally, if we assume the eigenvalues of A should be less than 4 times eigenvalues of, so basically it is, instead of A I can write this here, dynamics or state feedback control and of the desired dynamics for server design. We'll go through all this stuff detail while having the example. Now let's go to the mathematical formulation, how we can find the all the details of in the observer analysis. So we have the system x dot equal to x plus bu and x naught y equal to cx plus du, and we have the observer dynamics x naught dot equal to a naught x naught plus b naught u plus l y. So let us define this the equation number 3, and this is equation number 4. Okay, so we are doing adding and subtracting e naught x on RHS of, okay, let me define another term here. Also we have e naught equal to, we can write x minus x naught, and e naught dot we can write x dot x naught dot. From this we can write e naught dot equal to ax plus bu minus a naught x naught minus b naught u and minus l y. Right. So now let us define this equation number 5. Okay. So now adding and subtracting x naught of equation 5, we are having e naught dot equal to minus a naught x naught minus b naught u minus ly plus ax plus bu plus a naught x. We are adding this term and subtracting a naught x, right? So from this we can write a naught x minus x naught plus x into a minus a naught plus u b minus b naught minus ly. And from this further we can write a naught, this is nothing but error. This is the error, x minus x naught. So we can write a naught e naught plus a minus a naught x plus b minus b naught into u minus ly. And now if you substitute in this equation y equal to, let us define equation 6, substituting y equal to cx plus du. In 6 we are having e naught dot equal to a naught e naught plus a minus a naught x plus b minus b naught u and minus, so if you substitute y here, in place of y, if you substitute this expression, we are having LCX minus LDU, right? And if you further manipulate this equation, you can write A naught, E naught plus A naught LCX plus B minus B naught LD into U. And let us define this equation number 7. Okay. And if you notice equation 7, E naught goes to 0 in steady state if all the eigenvalues of E naught are negative or staying in the left-hand spline. And at the same time, if these matrices are 0. Okay. So please, I'm repeating again. To make E naught to 0. So all the eigenvalues of A naught to be negative, and this term, this matrix and this matrix should be 0 at the time. So we can write E tends to 0 as t tends to infinity if EIC of A naught are negative and A minus A naught minus LC equal to 0 and B minus B naught minus LD equal to 0. So from this equation, so if this condition are satisfying, and at the same, also you can write from this equation A naught equal to A minus LC and B naught equal to, we can write B minus LD. Okay, this you can write from this equation, you can write, and from this equation we can write. Right, now, and if you substitute this condition, if you substitute this condition and this condition in equation 7, what you are getting? So substituting above conditions in equation 7, we have E naught dot equal to A minus LC X naught, sorry, E naught This is the expression we are getting, and let us define this equation as 8. Now, if you substitute, if you substitute this term, this condition in the observer dynamics, what is written here? So substituting A naught equal to A minus LC and B naught equal to B minus LD in equation 4, we get full order observer. In the equation, you can write x naught dot equal to a minus LC. In place of a naught, you can write into x naught plus b minus LD u plus Ly. And also you can simplify this expression a x naught plus bu plus L into y minus cx naught minus du. So that is equation number 9. So here, the term here we call, this term we call residual term, and which can represent as, so this is basically a residual and which can be represented as y minus cx naught minus du equal to, in place of y you can write cx plus du minus cx naught minus du. So this cancel, and we can write c into x minus x naught. So this is nothing but error e naught, right? So we can write c e naught. So if you notice carefully, if residual term goes to 0, if error dynamics E naught dot goes to 0. So this is the condition, right? And as t tends to infinity. So in this condition, and hence we can say system is asymptotically stable. So this here system is nothing but the estimation error dynamics. So estimation error dynamics. So this is how we can design the observer dynamics or estimation error dynamics, and how we can validate whether how many states are available in the output, which will be used to design the state feedback control. And this is the full mathematics to come out with the error mix between the actual and the observer values from the sensors. Now, if you want to see the closed loop diagram, so we can draw the closed loop diagram of the system. So here, if you consider y equal to cx, sorry. So let's assume the most practical one. So here we can write system is x dot equal to ax plus bu and y equal to cx. For example, we don't have the du part, and the observer dynamics, let's assume the observer dynamics here. This is the observer dynamics. So from this we can write from equation 9, x naught dot equal to ax naught plus bu plus L. If you assume du part not there, this du part we assume to 0. So we are making some simplification in this dynamics. So here L into we can write y minus cx naught, right? Now, if you want to draw this control diagram, how the system it can be design the closed loop block diagram. So we have the B matrix. First, let me draw the figure. B, summing point. We have the integrator 1 upon S. This is C matrix, and we are getting output Y. And we are having the feedback here. A, this is X, this is X dot, and let's assume we are having U here, and this is the feedback, and this is basically positive, right? So from this equation, you can write X dot equal to AX plus BU and Y equal to CX. Y equal to C into X, and X dot equal to AX plus BU, right? Now, here also we need to have the observer dynamics. Here, so here we are taking the output here, and we are having comparator, one comparator which compare the output from the original system, and we have the observer gain matrix here, or L. This is coming here, and this is goes to another summing point, B, and this is the control is coming here. And so this is this part I'm drawing based on this dynamics. Okay, and we are also having from this we are having another block 1 upon S. This is X naught dot, this is X naught, and we are getting multiplied by C, which is giving Y, observed Y output, and this is negative. And we are having also A matrix here. A is here, is coming from the X naught, and we are having feedback here plus. And so here, if you tally with the system, so Y naught is nothing but CX naught, right here. So let me define it. So here, first I'll find this term, L into Y minus CX naught, and this is the BU term, which is going to extort dynamics, and also we have AX naught. This is AX naught. So this is basically, we can say, full order observer figure. Full order. So this is how we can come up the full observers for the system, and we can see how we can do practically for a system. The next lecture will be taking one example, how we can do the observability of the system, and how can come up the aerodynamics, and how we can find the, because here the most critical part is finding this L, the gain, observer gain matrix. So we'll do all this stuff in our next lecture. Thank you.